this point over here is f evaluated at A, big F evaluated at A, and this point over here is big F evaluated at B. Right, so those are the endpoints. This is a point of coordinates A and big F at A. This is a point of coordinates B and big F at B. Okay, so far so good? Okay, now I know that somehow I am going to get to that area. So somehow I know I need to, the left side here tells me that somehow I need to get from integral from A to B, right? So that means I need area under the graph of small f, right? It's not there yet. We don't know where that graph is. But because I am talking about the area between A and B, the area under the graph of small f, area under the graph below small f between A and B, I know that that area is connected with the idea of splitting the interval AB into n sub-intervals, right? So let's do that. We know from yesterday, from general Riemann sums, that when I split the interval AB does not need to be into equal intervals. So as you can see here, I am splitting my interval AB into n sub-intervals that are not of equal length. So I placed here x1. Do we see x1? I placed here x2. Then before B, I have the point x at n minus 1 and x at n minus 2. Is that correct? And of course, A is my x0. A is my x0 and B is my xn. From x0 to xn. So far, so good? Am I okay, ladies and gentlemen? Good. So now let's see, because I have these points x1, x2, and so forth, x at n minus 2, x at minus 1, and x at n. Of course, it makes sense to look at the corresponding y coordinates. Let's draw together the corresponding y coordinates. So what is so I have my point x1 here. My y coordinate right here is going to be, of course, big F evaluated at x1. I could show it here on the y-axis, right? Or I hope you don't mind that I am going to show it here on a vertical line. You're going to see in a second why. Tell me, please, if I'm okay with what I'm doing. I pick my points. I have my partition there. I partitioned the interval AB into n unequal sub-intervals, and I am looking at the corresponding y values. The corresponding y values are f at x1, f at x2, f at so on and so forth. The last three are f at xn minus 2, f at xn minus 1, and f at b, which is the same as f at xn, right? So I did the partition, and I showed the corresponding y interval. We know how, the corresponding y value. Am I okay? Am I okay? Yes? Good. So now, ladies and gentlemen, we're going to start here from the right part of the fundamental theorem of calculus. Right over here, this is the right part. F at b minus f at a. I'm going to start with that part over here, right? So I'm going to start from here and move my way towards the left part. So in the end, my proof I have to manipulate the right side until I get to the left side, right? So let's see on the graph, what is the meaning of f at b minus f at a? What's the meaning, graphically, what is the meaning of f at b minus f at a? What's the meaning of that? What is the meaning of that? Let's take a second to think. What is it? It has a very specific meaning there. What is it? On my graph right there. On my graph right there. What's the meaning of f at b minus f at a? For example, who can help me from home? Let's see. Nikhil.
It's the vertical length between f at a and f at b.
Be more specific. Look at my graph and be more specific there.
So then I guess the sum of f at x1, f at x2.
No, you're being more overcomplicated. No. Be more specific on my graph. My graph is given there for a reason. What is f at b minus f at a? Be more precise, please, based on the graph that you see in front of you. What is f at b minus f at a? It's right there. Yes, describe it with more words. What vertical line? I see lots of vertical lines. Which one is it?
The vertical line on the y-axis.
Describe it with more words. Describe it. It has something specific, the vertical line. On purpose. What's specific about that line? It's a segment, actually, not a line. Nevertheless, what is it? How can you describe it?
It extends from f at a to f at b.
Yes, and on my graph, it extends from f at a to f at b, yes, and it is a, what kind of line?
Vertical line.
It's vertical, yes, and more on my graph, it has something specific to be so obvious to you. The segment between f at a and f at b. What's specific to that segment?
Sticker, it's red.
It's very red, yes, so you can see it, and it's obvious, a red segment. So f at b minus f at a is so obvious, it's that big red line, yes? So we can see it and recognize. That is f at b minus f at a. So that's my starting point over there. Are we in agreement with that? Good. Now, how can I write that? Well, I hope you agree that the red segment over here, this one over here, is nothing but the sum of all these small segments on that I showed over there. Is that correct? Is that correct? Yes or no? So how can I write the red segment? The red segment is the sum of blue and green and lots in between and small red and black over there. Is that correct? Good. Now tell me, please, how do I write the blue segment over here? How do I write the blue segment over here? How do I write the blue segment over here? What's the length of that blue segment? Yes, Nimrit? For sure, it's f at xn minus f at xn minus 1, right? How about the green segment over here? Jocelyn, how do we write the green segment over there? F at xn minus 1 minus f at xn minus 2, correct? And so on. How do I write my red line over here? A red line over here. Let's see who's helping me from home. Jeremy, red line.
f at x2 minus f at x1.
Excellent. And the last one, the black segment over there. Who's going to help me with the black segment over there? From home?
f at x1.
F at x1. F at x8. I mean f at 8. F at 8, or in other words, f at x0. Good. Okay, so now let's write that in using algebra. So f at b minus f at a can be written as blue segment plus green segment plus red segment plus black segment. So based on what you guys told me, it's going to be something like that. I wasn't consistent with this one should have been a red. So this is a red one. Based on the color of the segments I used, this should be the red. Good. Okay. So black segment plus green segment plus another black segment that I didn't show, plus the last two, red and black. Are we okay with that? Exactly as you told me in words, I write now in mathematical terms. Am I okay with that? Am I okay? Yes. Yes, we are good? Good. So I am going to write this using sums as sum with I, f at b minus f at a will be sum with I going from 1 to n of f at xi minus f at xi minus 1. Let's see what happens there when I is 1. First term would be f at x1 minus f at x0. Yes, I'm good there. That's the first term I want. And the last one, when I is equal to n, is going to be f at xn minus f at xn minus 1. So yes, indeed, that's correct. So I just use the summation method. Yes, ladies and gentlemen. Am I okay, ladies and gentlemen? Am I okay? Am I okay? Good. Okay, so what I am going to assume is that this big F is a continuous and differentiable function. I think that's a safe assumption. Good. So now let's take a look together at the following. Let's apply the okay. Good. Okay. So what I am going to assume is that this big F is a continuous and differentiable function. I think that's a safe assumption. Good. So now let's take a look together at the following. Let's apply the mean value theorem on the interval, on a small interval, on this interval. On each of these intervals, because the function is continuous and differentiable, I can apply the mean value theorem on that small interval, right? The mean value theorem tells me that slope of secant, right over here, slope of secant through the endpoint. Let's understand, is that indeed slope of secant of the endpoint? Is that? Yes or no? Yes, it is. Must be equal. I'm going to find a point. I am going to find a point within that interval so that slope of secant is equal to slope of tangent. Mean value theorem tells me loud and clear that within each interval, if I'm applying the mean value theorem on each interval, I'm going to find a point, a certain point. I call it Ci, so that the slope of the tangent is equal to the slope of the secant through the endpoint. Is that correct? Good. So that this part over here tells me that I can do the same thing on each interval, on each of these intervals. Let's take this interval over here. The intermediate value theorem tells me that slope of secant, which is this one, big F at x2 minus big F at x1 divided by x2 minus x1, that's the slope of the secant, will be equal to, I'm going to find a certain point, let's call that C2, such that the derivatives, well, C2, I guess in this case is somewhere over here, right? But doesn't matter, it really doesn't matter. But what matters is slope of secant will be equal to slope of the tangent. Okay, and I'm going to repeat the same thing on each interval. So on my first interval, x0, x1, I'm going to find a certain point, C1, at least one point. On my second interval, x1, x2, I'm going to find a point, C2. Yes? On my last interval, xn minus 1, xn, I'm going to find the point, Cn. On the previous interval, I'm going to find the point, Cn minus 1, right? Is that true? Yes or no? Okay, so let's see where we are, ladies and gentlemen. Where are we? We see here that based on what I got, I only have f at one endpoint minus f at the second endpoint, right? So that makes me say from the mean value theorem applied on a certain interval that that relation can be rewritten like that. Is that correct? Good. Is that correct? F at xi minus f at x minus xi minus 1 will be written as f prime at ci times xi minus xi minus 1. Is that correct? For sure it is correct, right? I just isolated this part over here. I haven't done too much. All I have done, I have isolated this difference over here because in what I started, those segments, that's what I had, right? Can I isolate? was able to isolate that. Good. So now let's go back to my, where I stopped, right over here. So this is where I stopped. I was at the point where f at b minus f at a is the sum of all those intervals, right? Okay, so what I wanted to do, I wanted to use mean value theorem as we discussed. Can you please use mean value theorem as we discussed? Please replace that difference with the expression we got from the mean value theorem. From the mean value theorem. Theorem, that must be bf prime at ci times xi minus 1. And now we jump up and down. What do I know about the big F prime? What do I know about? Show me somehow with your hands. What do I know about the big F prime? What do I know? Show me with your hands. Show me with your hands. Show me. Somehow make me understand, Visha. Make me understand, Kubi. Alec, make me understand there. Big F prime. What do I know about big F prime? Big F prime. What is big F prime? What is big F? Big F prime, the derivative of big F. What is it? What is it? What is it? What is it? Yeah, a good idea would be to write on a piece of paper, because obviously with your hands, you guys are okay. You are not doing a very good job. Actually, you know what? That's a very good idea. You're gonna have some post-it notes close to you. That's a fantastic idea, guys. More opportunities for you to collaborate, to contribute in class. Have post-it notes for me. Yes, hands are good, but sometimes that's fantastic. Yes, it's fantastic. Yes. This is a critical part of this. Big F is not prime. The derivative isn't that how I started. Big F prime, right? When I differentiate that, I get the function f of x, right? That's exactly what happens over here. So big F will be f at ci, so small f at ci times xi minus 1. Are we okay at this step? Critical step. Good. So now, ladies and gentlemen, all of a sudden, we started with the conversation about big F. And now I want you to think for a second about the meaning of what we have obtained right over here. What have we obtained? Look at that. What is that? Forget about the sum, just that part over there. Take a look and again, use your post-it notes and tell me the meaning of that. Have we seen? Imagine the function small f independently from that and tell me what's the meaning of this. Just this. That's all I want. I don't care about anything else. I only care about the meaning of this and nothing else. Meaning of this. We take a minute to think about that. Write on that post-it note. But right now we are still thinking. 1 minute, we are still thinking. What's the meaning of that? F at ci times xi minus 1. What is that? What is that? Let me see what I can see in your answers there. So now you can put your answers there. You can put your answers right over there. Show me what you have there in front of. Be more precise, Shrabi. Very good. Very good. I want to see. Be more precise there. It's an area of a rectangle. Exactly. It is. What's the length of that? What's the width of that rectangle? Of course, is xi minus 1. What's the length? Is f evaluated at ci. Ta-da! So what have I accomplished? Something fantastic I have accomplished. A window. I want to share this window. Good. So what do I have there? I have area, all the area under what curve, ladies and gentlemen? Under what curve? Over here, if I keep adding areas, all the areas from 1 to n, what do I have? I have the area under the curve. What curve? Small f. Small f, right? I'm talking about the small f there. Okay, well, I'm skipping a few. I'm showing here that I'm skipping a few steps. I should have made more and more intervals, send n to infinity, but doesn't matter. I skip those steps. What matters is that what I have there is a Riemann sum. For the small function f, this is what matters, with a partition P using the set of sample points C, or in other words, is integral from A to B, definite integral from A to B of small f of x dx. Small f of x dx. Yes? Good. So right now we take 10 minutes. So I ended up exactly where I wanted, connecting the two i's